When Toyota introduced the third-generation Tundra with its all-new twin-turbo V6, expectations were replacing the legendary 5.7-liter V8 with a smaller, more efficient, high-output, turbocharged engine was a bold and technically impressive move. But as real-world ownership data accumulated along with teardown analysis and warranty reports, it became clear that the original engine block was being subjected to stresses. It had not been fully optimized to endure under certain operating conditions. By the time development of the 2026 Tundra was finalized, Toyota engineers had spent years quietly re-evaluating the block from the inside out. The result is not a simple material change or software update, but a fundamentally reinforced block architecture designed for long-term durability, structural stability, and thermal resilience. This video explains exactly how Toyota strengthened the 2026 Tundra's engine block, why those changes were necessary, and what mechanical engineers say about the effectiveness of the redesign. Rather than over-engineering the entire block and adding unnecessary weight, Toyota focused on targeted reinforcement. The goal was to increase rigidity where stress concentrates, improve load distribution, reduce microdeflection under peak torque, improve resistance to thermal distortion. Every major structural element of the block was reconsidered. One of the most important changes involves the cylinder walls. The original block used relatively thin walls to save weight and improve cooling under sustained boost. However, those walls exhibited microscopic flexing. Over time, this can degrade ring sealing, create uneven wear, and form localized hotspots. For 2026, Toyota selectively increased wall thickness in the upper and mid-cylinder regions. Instead of uniform thickening, engineers reshaped the walls with ribbed internal contours that resist expansion while maintaining coolant flow. This geometry-based reinforcement keeps the cylinders rounder under load, improving piston stability and long-term compression integrity. The main bearing webs form the backbone of the engine, anchoring the crankshaft and absorbing enormous combustion forces. In high-torque turbo engines, especially at low RPM, these loads are extreme. Analysis of early engines showed micro-movement in the webs under repeated high-load cycles, which can lead to bearing wear, oil film breakdown, and eventual crank alignment issues. For 2026, Toyota increased web thickness, enlarged fillet radii to reduce stress risers, improved load transfer between the webs and block skirt. The result is significantly higher torsional rigidity and better crankshaft alignment under full torque. The lower block skirt plays a key role in resisting twisting forces. Turbocharged engines experience asymmetrical loading during boost, and insufficient skirt stiffness can allow subtle block distortion. Toyota redesigned the skirt geometry, adding material only where stress analysis showed it was needed. The skirt now integrates more tightly with the main bearing caps, creating a single unified load-bearing structure that improves structural continuity and reduces fatigue-inducing stress peaks. The block remains aluminum for weight and efficiency, but the alloy formulation was revised. Silicon content and trace elements were adjusted to improve strength and thermal stability, and the heat treatment process was refined to produce a more uniform grain structure. The result is greater resistance to cracking, improved fatigue life, and better dimensional stability under heat without making the block brittle. Structural reinforcement alone is not enough in a turbocharged engine. Heat management is equally critical. For 2026, Toyota re-engineered the cooling jacket layout to improve flow around the upper cylinder walls and exhaust side regions, reducing localized hotspots and lowering thermal gradients across the block. This minimizes expansion-contraction stress and helps preserve long-term dimensional accuracy. Testing shows that the reinforced block exhibits measurably less microscopic deflection under simulated towing and sustained boost, reduced microflexing improves bearing life, oil film stability, piston alignment rings, seal durability. In practical terms, the engine maintains tight mechanical tolerances for much longer under heavy use. Independent powertrain engineers describe the 2026 block as a classic second-generation correction, where real-world failure data refines an already competent design. Rather than chasing higher horsepower, Toyota focused on durability at existing output levels, particularly for towing, hauling, and high-temperature operation. For real-world drivers, the reinforced 2026 block promises greater long-term durability, improved thermal stability, reduced risk of block-related wear, more consistent performance at high mileage. Toyota has not heavily advertised these changes. Publicizing structural fixes can inadvertently validate earlier concerns. So instead, the company has chosen to let long-term reliability speak for itself. The 2026 Tundra's reinforced engine block represents a data-driven structural correction, not a cosmetic update. Through optimized cylinder geometry, strengthened main webs, improved alloy metal, redesigned cooling passages, and increased lower block rigidity, Toyota has addressed the core mechanical challenges of a high-torque twin-turbo V6. From an engineering perspective, these changes significantly improve the engine's ability to withstand sustained load, thermal stress, and long-term service. This is not just an update, it is a structural evolution grounded in real-world engineering reality.